Welcome to the lecture series on computer architecture and organization. In the last lecture, we saw about this addition and multiplication. In addition, we saw about the addition instructions, that is the set of instructions that is executed by the MIPS in order to check for the overflow. And in multiplication, we saw some algorithms and we saw some hardwares that are in the previous version as well as the refined versions of the hardware we have seen. And today's class we are going to see about this division algorithm. So if you see this code that is divided emperor, it is a Latin term which means it means divide and rule. So in this lecture we are going to see about this division, how it divides and rules the computer architecture, the computer design. So this is a long division example. So if you come for this long division example, uh, first we want to know about the operands of the division. So what are all the operands of the division? It is divisor, the number that divides another number. So that is the divisor. What is that another number or the number that is being divided? That is the dividend. And quotient is that how many times the divisor fits into the portion of the dividend. That comes for the quotient. And the remainder, if it doesn't fit, if it generates some remainder, then that is the remainder part we are getting. So this is our simple long division algorithm which we could have studied in our old school days, and this is the simple rule which we need to follow when we perform this division algorithm. That is the divisor. Divisor is equal to quotient into divisor plus remainder. So this is a very simple rule. Before we getting into this algorithm, you should know about this division algorithm. So if you see this example, so the dividend is 1 0 0 1 0 1 0 and the divisor is 1 0 0 0. So this 1 0 0 0 fits one time inside the first 4 bits of the dividend. So we have kept this 1 into 1 triple 0, which is equal to 1 triple 0. Now the operation is subtraction. So when we subtract, we get the intermediate result as 1 and we need to get down the 0. So it is 0 again. Again, if we compare this intermediate result with the divisor, it is smaller than the divisor. So what we should do, we need to add one more 0 here and we need to drag down another digit down. So similarly, we need to iterate this until this intermediate result becomes greater than or equal to the divisor, so that the divisor fits into the portion of this divided result. Okay. So this is the old algorithm which we all know. So this is the first version of the division algorithm. So the first version of the division algorithm, which includes a divisor of 64-bit register and a quotient of 32-bit register and ALU, that is arithmetic and logic unit of 64-bit registers, and remainder which also includes 64-bit register. So this control test was what this control test do is that it controls all the operations that is being done on divisor, on quotient, on arithmetic and logic unit registers and remainder registers. Okay. So this is a division algorithm that is used by a hardware. So first we need to start this algorithm. First we need to start, and later after we have started we need to do the first step. So subtract the divisor register from the remainder register and place the result in the remainder register. So first step is that we need to subtract the divisor register from the remainder register and again we need to place it in the remainder register. And the next comes this decision part. So it tests the remainder whether it is greater than or equal to 0 or less than 0. Okay. So what is the need of this portion is that it needs to check whether the intermediate result is greater than the divisor part or less than the divisor part, or whether it is positive or whether it is negative. Because unlike humans, the computers cannot directly check by seeing whether it is greater than or not. We, the humans, can directly interpret a number and we can say this is greater than this number and this number is greater than this number. But computers can't do directly. So it performs a set of operation, and that operation is checking the remainder whether it is greater than or equal to 0 or less than 0. So if the intermediate result is greater than or equal to 0, that is positive, then what is the operation? This is 2a. The operation is shift the quotient register to the left, setting the new rightmost bit to 1. So if not so, restore the original value by adding the divisor register to the remainder register and placing the sum in the remainder register. Also, shift the quotient register to the left, setting the new least significant bit to 0. So these are all the two operations after we are checking. We will perform any one of the operations depending upon the result that is done by this testing condition. And the third step is that we need to shift the register, that is the divisor register, right by 1 bit, because we need to shift the divisor part so that we can get the dividend portion sum. Okay, how many times the divisor gets into the dividend portion. And very simplest thing about this algorithm is that we are playing only with ones and zeros. So this division algorithm is called as binary division algorithm. And next thing is that we need to check the repetition at how many times we have repeated this operation. So we will check whether this is the 33rd repetition. The beauty of this division algorithm is that surprisingly we are having one more step than the multiplication algorithm. In the multiplication algorithm we have performed 32 iterations, because we saved the product in 32-bit register and we checked only up to the 32nd repetition. But here we are having one more repetition, that is the 33rd repetition. So the algorithm checks whether it is the 33rd repetition or not. If it is not so, then the loop continues from the starting point. If so, it comes out of the algorithm and it ends the algorithm. Okay. So now let's crack this division algorithm. So using a 4-bit version of the algorithm to save pages, let's try dividing 7 to the base 10 by 2 to the base 10, or 7 in terms of binary, it is 0 0 0 0 0 1 1 1 to the base 2 by 0 0 1 0 to the base 2. Okay. So here there should be another base. So this is to the base 2. So this is the tabulation to perform this division algorithm. If you see here, this is the iteration numbers. So these are all the iteration numbers 0, 1, 2, 3, 4 and 5. We are performing 4-bit in order to save the pages, but we are in need of one more iteration step in division algorithm, hence it is the 5th step. Okay. And these are all steps. First we need to do this initial value, and this is about the quotient, this is about the divisor, and this is about the remainder. Very important thing about this first loading the system is that, or loading the hardware part is that, in the remainder part we need to save the dividend, the content of the dividend into the remainder register. And taking this divisor part, it is an 8-bit register, because there may be some extra bits that may be come into that. So it is an 8-bit register. And one more important thing in this divisor register is that we need to load this in the left half of the logical part or the register part, because we want to shift every time the divisor to the right. So if we want to shift it to the right, then it should be placed in the left half of the register. So the divisor is always loaded in the left half of the register, and the remainder, that is the dividend part, is always being loaded in the right half of the register. Okay. And quotient, it is initially loaded to 0 0 0 0. So let us crack it. coming to this point, this is a quotient register 0000 and divisor is 00100000 and remainder that holds this 00000111. Okay, the first thing is that we need to do this remainder part, that is remainder is equal to remainder minus divided. So we need to fill this part. So subtraction can be performed directly by this borrow method, or the subtraction can also be performed by the 2's complement method. So if we negate this number, that is the divisor, negating in the sense if we take 2's complement for this divisor, we can add this to the remainder. So already we have seen in the addition and subtraction part that subtraction is a tricky part to addition. Okay. So instead of doing subtraction, we can negate this divisor part. We can negate in the sense we take 2's complement for this and we are adding this number to the remainder part. Okay. So let us do this. So this is a divide. So this is a remainder part. Okay. So remainder is 000011. So this is a remainder. And what about our divisor? Our divisor is 00100000. So if I want to take this, let me do it again. So if I want to do this division, this is our divisor part. If I want to take 2's complement for this, so first thing is that 1's complement for this will be, 1's complement will be, or 1's complement in the sense we want to negate all the zeros to 1's or invert. So 0 change to 1, 1, 0, 1 and again 1, 1, 1, 1. So if I want to perform 2's complement with this, what I must do? I must add 1 here. That is to the least significant bit. So this is a 1 here. So I must add both these things. So if I add here, what is the operation comes? So it comes to 1 plus 1, 0. So it carries 0, it carries 1 again. So it carries 0. 1, 1 plus 1, 0, 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 and again here it will be 1, so it goes to 1, and again it is 1, and again it is 1. Okay, so it should come like this, should align like this. So this is a divisor's 2's complement. Divisor is 2, so this is negative 2. So we have taken negative 2, we need to add this negative 2 to this remainder part. Okay. So if we add this to the remainder part, what we will get is that the remainder is 0000011. I want to add this with this part. I want to add this to this one. Okay. So if I do like this, what I will get if I add, so there is no carry, I can easily add this. So how can I add? Actually I should add from least significant bit, since this result, this sum doesn't generate any carry, I am doing it from left side. So it is 1 1 1 0 and 0 1 1. So this is the result. So this is the result. I must copy and I should place this in this register. Okay, so 1 1 1 0 and 0 1 1 1. What is the value of this divisor? The divisor will be as it is, because the first step says that remainder is equal to remainder minus division. So divisor remains the same. So 0 0 1 0 0 0 0 0, and the quotient also remains the same. So 0 0 0 0. Now we have come to the second point of this algorithm, that is we need to check whether it is greater than or equal to 0 and less than 0. Okay. So if we check this, how can we check? We can check this most significant bit. If we check this most significant bit, it is 1. So obviously if it is 1, it means it is negative, because in signed integers, if the most significant is 1, it is negative. If it is 0, then it will be positive. Okay. So what I must do is that since this is negative, I must go for, if this is negative, I must go for this 2b. So what this 2b says that I need to 2b says that I need to restore the original value by adding the divisor register to the remainder register and placing the sum in the remainder register. Also, we need to shift the quotient register to the left, setting the new least significant bit to 0. So now I am setting here. So what is the next step? I must add these. So if I add, the result comes to 0, 0, 0, 0 and 0, 1, 1, 1. Okay. What I must do, the divisor remains the same, 0, 0, 1, 0, 0, 0, 0, 0, and I want to, next is I want to shift the quotient, that is I must shift the quotient to, here see here, shift the quotient register to the left. So I must shift it to left. If I shift this to left, then it becomes 0, 0, 0, 0. Next step. So I have performed the operation in 2b. So what is the operation in 2b? I want to restore the original value. How can I restore the original value? I must add the divisor register to the remainder register and placing the sum in the remainder register. So I have added both this divisor and remainder, and I have placed the resultant remainder register. Also I have shift the quotient to the left of the register. Now the next step is that I need to shift it to shift the divisor to the right. Okay, so it should be divisor. I must divisor to the right. Okay, so if we shift it to right, then this one that is from the MSB, it is in third position, it will be shifted to fourth position. So 0, 0, 0, 1, again it will become 0, 0, 0, 0. Okay, and the remainder remains the same, 0, 0, 0, 0, 0, 1, 1. Okay, and the next step, what I must do, I must do remainder is equal to remainder minus divisor. So what is this remainder? So remainder, we are having 0, 0, 0, 0, 0, 1, 1, 1. I must subtract this divisor from this remainder. So what I can do, I can negate all this and I can add 1 to this, and I can directly add this with this remainder number, that is taking the 2's complement of this divisor and adding to the remainder. If I do the previous step as I have done, then what is the result of this? It is 0, 0, 0, 0, and again it comes to 0, 1, 1, 1. Okay, now these remains the same, 0, 0, 0, 1, 0, 0, 0, 0, and this too remains the same, 0, 0, 0, 0. Now I want to check again whether the remainder is less than 0 or not. Okay, so if this this must be the answer like this, that is 1, 1, 1, 1 and 0, 1, 1, 1. After adding and placing, after adding in the sense, after we need to restore the original values. So restoring the original values in the sense, if you compare this result, that is 1, the result of the remainder, and in the next step also we have got the same result, because we are restoring the original value by adding the divisor with the remainder and placing this, because if it is less than 0, it makes no sense, because the quotient will be always 0. So this step is iterated like this, and this step doesn't has any change, and this too doesn't has any change. Now if you check the result, it is 1, again it is less than 0. What if less than 0? What I must do, I must do this, I must add this divisor to the remainder, and I must place this divisor. Sorry, I must place this in this. I want to place this in this. I want to place this in this reminder register. Okay. So what is this operation? This is 1. So since this is 1, this is negative. So what I must do is that I must add the divisor register to the reminder register and place the sum in the reminder register. So if I do like this, then what is the next step answer? It will be 0 0 0 0 and 0 1 1 1. Okay, and the next step what I must do is that also I need to shift the quotient register to the left, setting to 0. Already it is 0, so there is no change in that. Okay, the quotient is 0 and there is no change in the divisor, so it is 0 0 0 1 and 0 0 0 0. Now I want to shift the divisor to the right. Okay, so if I shift like this, then it comes to this part, that is 0 0 0 0 and 1 0 0 0, and all other remains the same. 0 0 0 0 0 1 1 1 and 0 0 0 0. Let me go up to the positive comes. Okay, so now again I want to do the next iteration. So what is that? Reminder is equal to reminder minus divisor. If I do like this, the answer comes to 1 1 1 1 1 1 1 1. So now all other remains the same, 0 0 0 0 1 0 0 0, and this also remains the same, 0 0. Now I want to again check whether it is greater than or equal to 0 or less than or equal to 0 by checking the most significant bit in the remainder register. So this is again 1, that is less than 0. So what I must do? I must add the content of the divisor register to the remainder register, and I must place here. Okay, so if I place here, what I will get? So I will get, what I must get is that it is 0 0 0 0 and 0 1 1 1, because I want to restore all the values. Okay, now what is this part? This will remains the same, divisor 0 0 0 0 and 1 0 0 0. Now I want to shift it to left, that is makes no sense, so setting the least significant bit also to 0. So if I shift left, it becomes again 0 0 0 0. Also q0 is equal to 0, that is the least significant bit is equal to 0. So the condition is that if we are getting a negative value, then we need to add the divisor with the remainder register, place the result in the remainder register, also shift the quotient to the left, setting the least significant bit of the quotient to 0. Okay, and next thing is that we need to shift the divisor register right. So all other remains the same. If I shift this to right, 0 0 0 0 0 1 0 0. Okay, and this result remains the same, 0 0 0 0 1 1 1. Okay, and next iteration. So the last the fourth iteration. The fourth iteration is I want to do reminder is equal to reminder minus register. If I perform this, then the answer will be 0 0 0 0 0 0 1 1. Okay, so now all other remains the same, divisor 0 0 and 0 1 0 0, and remainder is 0 0 0 0. So now I want to compare whether this is greater than or equal to 0 or less than 0. So this is greater than 0 because the most significant bit is 0 here, and this is positive. So if it is positive, then I must go for 2a operation. So what is 2a? It says that shift the quotient register to the left, setting the new rightmost bit to 1. Okay, what I must do? Just I want to shift the quotient bit to the left, and I want to set the least significant bit, that is the q0 to 1. So it becomes 0 0 0 and 1. All other remains the same. Okay, so what is in the step? It is 0 0 0 0 and 0 1 0 0, and this remainder 2 remains the same. Next I want to shift the divisor register to right. So 0 0 0 0 0 0 1 0, and here it remains the same 0 0 0 1, and this part remains the same. Okay. Now the fifth iteration, that is the last iteration. So the last iteration starts with the remainder part, that is the quotient part 0 0 0 1, and divisor remains the same. So 0 0 0 0 0 0 1 0. What I must do here, it is remainder is equal to remainder minus divisor. So if I do like this, it comes to 0 0 0 0 0 0 0 1. Okay, so now again checking the most significant bit of the remainder register. It is greater than 0, it means it is positive. So if it is positive, what I must do, just I want to shift the quotient register to the left, setting the new rightmost bit to 1. So I want to shift it to the left. So if I shift the quotient register to left, so this one comes to the 1 which is in the least significant bit. From the right, it is in the first position, it comes to second position from the right. So 0 0 1, again I must set this q naught to 1. Okay, so this is 1, and the divisor remains the same 0 0 0 0 0 0 1 0. Again the remainder remains the same with 0 1. Okay, now I want to shift the divisor to the right. So shift the divisor to the right in the sense 0 0 0 0 0 0 1, and the quotient remains the same 0 0 1 1, and remainder is 0 0 0 0 0 0 0 1. So we can easily check this validation in the decimal part. We have divided 7 by 2. Okay, so 7 divided by 2. So 7 divided by 2, the quotient will be 3 and remainder will be 1. So if you check the quotient register, it is 0 0 1 1, which is the binary equivalent for 3, and remainder it is 1, which is the binary equivalent for 1. Okay, so the answer is correct in our algorithm. So let me recall this algorithm. So first step is that we need to do this remainder is equal to remainder minus divisor. So we need to check, we are doing this step in order to check whether the intermediate result is greater than or equal to 0 or less than 0, or in alternate way we can say whether it is positive or negative. So next step is that if it is positive, then we need to do one set of operation. If it is negative, then we need to do for next set of operation. So if it is negative, so what we should do, we should restore the original values of the register by adding the divisor register to the remainder register and placing the result in the remainder register. Okay. Also we need to shift the quotient register to the left, setting the new least significant bit to 0. So we should not forget this part, that is q naught is equal to 0. And the next iteration is that we need to shift the divisor register to the right. Okay. So if this is for negative part, if we come for positive part, that is only one operation. What we need to do is that we need to shift the quotient register to the left, and we need to set this q naught to 1. That's all. We need not to restore the original values, because if we have a quotient, then the register value will be different. So these are all the two set of operations under the conditions we are doing. Okay. So coming to the next part. So this is a revised version of the division algorithm. So if you see here that quotient register has gone, okay, the quotient register is gone, and the quotient register, if you the quotient register, it is placed in the left of this 64-bit remainder register. Okay, and the divisor register is only 32 bits, and ALU is of 32 bit. Compared to the previous version, it is of 64 bit. Okay, whereas we are having only the 32 bit here, and the control test operation tells when we need to shift this divisor register and when we need to shift this quotient register. Everything that is controlled by this control test registers. So coming to the point of sign division, the simplest solution is to remember the signs of the divisor and dividend and then negate the quotients if signs disagree. Okay. Correctly signed division algorithm negates the quotient if the signs of the operands are opposite and makes the sign of the non-zero remainder match the dividend. So if you go for this signed operation, the one thing you need to keep in mind is that we need to make the sign of the non-zero remainder match the dividend. Okay. And this is the comparison between this multiplication and division part. If we come for this multiplication part, we have a pair of 32-bit registers to contain the product and a 32-bit ALU. Whereas in division part, it has a 64-bit register to shift left and right and a 32-bit ALU. And the next is that we are having this high and low registers. So the high and low register, this is in order to keep the two 32-bit product. And here the high and low registers, the high has quotient and the low register has the remainder part. And coming to the point of this unsigned instructions, mult and mult u are for unsigned instructions. Here this is div and div u for unsigned instructions. And these are all the two registers which we need to transfer the content, and from there we are need to fetch. Okay, so with the help of this pseudo instructions, with the help of this pseudo instructions that is generated by the MIPS, we can fetch the instructions that are stored in the result register with the help of these two, that is MF low and MF high. Okay, so the MIPS assembler here. Here also we are having MF low and MF high. The MIPS assembler allows divide instructions to specify three registers generating this MF low and MF high instructions to place the desired result into a general purpose register. Okay, so that's all about this division algorithm. Thank you for watching. Keep watching.